Okay, so who was at the talk yesterday? So, a quick recap. We talked about associations, which is like a new variant, a new kind of data structure that will become a big part of everyday Mathematica expressions, like lists. I'll very, very quickly run over what we covered. So associations are associative arrays. They're similar to Python's dicts and dictionaries and C++'s hash maps and all this kind of thing. They allow you to associate values to keys. You can easily, once you've done that, you can easily look up the value associated with a key. And if it's not there, it will return missing. You can also explicitly give an expression to evaluate if the key is not found. So we could say, not found. But if this was an A, then we'd get 20. So that expression is held until, and that means you can do cool things like if there's some expensive default, you can only compute it when it's actually necessary. Then we covered all the different ways you could create associations. So the basic one was combining lists of rules or other associations with a conflict resolving function. And it's the job of that conflict resolving function to decide how to deal with values that share the same key. Then we looked at organized by, which is a way of turning an ordinary list into an association. You give it kind of what part of the list you want to become the key, and also what it is you care about in the list, because you don't want to duplicate the key both in the key and in the value. Or you can provide a function that defines the equivalence class, like the length of a string, so that all strings of length 3 end up as a list in the association under 3. So we dealt with some of that. Then now I'm going to get to this mysterious thing that I deliberately skipped over last time. So this is the beginnings of a type system for Mathematica. But it's specifically a type system for data. So we've done well as a dynamically typed language. But there are certain kinds of role or task that a type system really is kind of quite crucial for. So a small program, if there's if you do something wrong and you end up taking part 3 of a string, it's okay if it fails. You can debug that fairly easily. But if you have some long computation that's running over a cluster, it's really not the right experience to have a job that's taking an hour crash at the half-hour point, and you fed with giant stack trace to try to find out what happened, or at least the poor Mathematica equivalent to a stack trace. So this is the beginnings of a type system, but it's specifically for data. And as such, it can be much simpler than what we would have to do if we wanted to fully type the whole of Mathematica. So let me get straight on to that. So yeah, there are a couple of philosophical things I could say. Like one of them is, where does large data come from? If we're dealing with large data, typically humans don't generate that much data. So you and me writing down in a Word document or pages or whatever, we can't generate data fast enough. There's a sense in which unstructured data is of lower volume than structured data. If it's big enough, it had to come from some automated process that's producing it, which means it will be structured. And in that sense, sort of big data by definition has to be structured. Otherwise, it wouldn't have been big. So once again, we can see as soon as it's structured, we can attach types, we can infer types. It's in our wheelhouse to think of it as types being important. And the last thing that I want to mention is I'm sure everyone here who's dealt with Mathematica has kind of come across this phenomenon that a lot of the work that you end up doing, mental work, interior work, is sort of reasoning about what some map will do, or what level you have to join something at, or how to transpose something to get it into the right shape. That's the bread and butter of a Mathematica programmer. We've solved all the easy problems. We have these wonderful primitives, but the real trick is to sort of plug them together in a way that sort of preserves the shape that we think they have. And typically when it goes wrong, Mathematica is not very friendly to you. So if you have some long list and you try to apply something to a part that's not there, or you try to map over a scalar. Actually, I think that'll work fine. I might be wrong about that. Let's try. if you say map f over 1, yeah, nothing happens. But there can be cases where, a good example is taking part 2 of a string. You can't do that. It would be string part. It would be string take. If that happens in the middle of some huge vector expression, then either you'll get like this expression's too large, and you'll see a tiny fragment of it and try to infer from there what happened. Or you'll get this weird phenomena where sort of Mathematica will partially evaluate something, and that partially evaluated chunk will snowball and sort of gather its own other partially evaluated things. Things go crazy. And it's very difficult to debug. It would be better if it sort of threw a hard error at the beginning. But what would be even better is if it stopped you writing incorrect programs to begin with. If you got the shape wrong, there might be enough information for us to deduce whether that shape is what you think it is, and stop you from doing something that's going to crash your computer or give you unhelpful messages. So how do we start this process? Well, we're dealing specifically with data, not with functions. We don't have to think about types of functions. Let's just think about types of data. Well, there are obviously atoms in Mathematica, and I'm sure everyone knows, atom Q of 5, that's true. But something like a list is not an atom. Okay, so let's introduce a basic set of primitives, set of atoms, but these are types, so the types of atoms. We have something like integer type, and I'll show you what that evaluates to underneath. This is, actually I have something called a type form, plain type form, yeah, okay. So I'm sort of hiding a bit of metadata that you shouldn't be seeing. So what is this underneath? This is kind of slightly odd. It's actually a compound thing. But that's because scalars are sort of the most important thing. That's like the leaves of your schema of some expression are going to be scalars. Strings, integers, booleans like true and false. And we kind of we don't really care. They don't have a shape. They just point-like. So the thing to really care about is the fact that they're scalar. And that's why there's this head. And then as an afterthought, it's what kind of scalar is it? It's an integer, or it could be, a real or a string or something like this. Now these format in a kind of funky way. I've played with lots of different formatting constructs. I'm not sure what the right sort of way of presenting the stuff is. Because you really need to see at a glance, what is the shape of this data structure I have? So this is my latest. It's like mathematical type syntax. I mean, it looks pretty simple. The first letter of the type, I for integers, S for strings, B for booleans. Then we have a weird thing. It's not really there's no enum in Mathematica, but that's okay, because this is more sort of philosophically, what is a list? If you had a list of M and F, the strings M and F, for male and female, in actual fact, they're strings, but philosophically, we know that they are from a limited alphabet. And that might even mean we could store it in sort of compressed form under the covers. And you'd never have to see that, but we'd be pulling tricks to make it be very memory efficient. And then when if you check for something male or female, then you might expand it out or something. And we could even have something in future versions of Mathematica where we take small strings and intern them into the kernel such that they only take a byte to store, even if we don't know in advance that they might come from a limited dictionary. There only are so many small strings. And then they can hash them, put them in a dictionary, and make them efficient to store. So this is sort of philosophically, if there's a list of things, like a list of A, B, 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 A, B, it's a string, but really it's from a fixed dictionary that's an enum type. It's weird, Collis challenged me at one point about this. He said, is this really a single thing, a single string A can't be of type enum AB. It's only in the context of many repetitions that you can tell that something's an enum. Okay. Oops. What is going on? This I don't like this whole slide sheet spread show thing. But they make me use it. Okay. So now the compound types. There are 4. There is list type. And that formats as just, can you guys see that? Let me do a bunch of enters here. So that formats as a list, it's more like a symbolic. Like this is a list of highs. Underneath, it's pretty much what you saw before. List type of scalar type of integer. Okay. That just means a variable length list, but they all have to be the same type. Then we have something called tuple type. And let me justify this for a second. So my claim is that lists in Mathematica have two very different sort of instantiations philosophically. Okay? One is a variable length list in which it's just as valid to have 5 in that list as 10. 5 things versus 10 things. So a good example would be, a list of similar entities. There could be 5 countries that you're interested in for some purpose. Like the G8 consists of 8 countries, but there's also like the G10, which consists of 10 countries. So there's nothing like conceptually that different. It's a list of countries. You can imagine it being quite valid to take a country out of G10 and put it into G8. Then you'd have G9, G9, but never. But a tuple is quite a different thing. In a tuple, it only, the meaning of a tuple is bound up in its size, and it's bound up in the positions of the elements in the tuple. So let's think of something like tally. Let's do, I don't know, random integer, 100, 1,000. Okay, so this is perfect because it combines these 2 points. The outer list is a genuine bona fide list. It can be any length, because we might have, if we'd done random integer 5, there'd only be 5 possible things that the outer list can. You guys know what tally does, right? Should I quickly? No one's going to admit to this. Anyway, so tally just returns the element and how many times that element occurred. So 3 occurred 174 times, etc. But the point is, the outer number is sort of it's not really intrinsic to the tally function. Depending on how many different exemplars there are, it will have, could be 5, could be 100, could be 26, so it's letters of the alphabet. But the inner lists of length 2 are always of length 2. And the first part always has the meaning, the item. And the second part always has the meaning, the count. It's kind of like there are different kinds of lists, even though they have the same data structure underneath them. Philosophically, they're different. So that's tuple. And the way that you write tuple type is like this. Tuple type of integer type, string type. That's perfectly legitimate to have 2 different types in this tuple. How much time do I have? 15 minutes. So, okay, so we have lists. What are the properties of lists? They are variable length. They are homogeneous. The types in the list are typically homogeneous. They're all, you treat them the same. The first thing is the same as the fifth thing. Tuples are very different. They're fixed length. They're heterogeneous. I don't know how to say that quickly, but they're heterogeneous or whatever. And it turns out this symmetry actually has an equivalent symmetry for associations, luckily. So let's look at what that would be. So if we have, remember, this is version 9. I get to do whatever I want here. So I have a little helper function called assoc, which is short for association. So let's say we have age goes to 25, name goes to Joe Stevens, I don't know, height goes to, what's a plausible height? 130 centimeters? I don't know American units. Someone help me. 180, okay. Okay, so this is a person, okay, in some domain here. And now we could obviously look up age and so on. But the key point is, if I were to make another version of it, if I was to make a second person, person 1, person 2, change things around, Jim Stevens. Okay, they're comparable. The ages are comparable, the names are comparable, the heights are comparable. This association is of fixed length. It really is analogous to tuples. It's exactly the same as tuples. Individual parts are comparable across examples, but not to other parts. And likewise, there's a fixed length. So what is the list version of an association? Does anyone have an intuition or can think of an example? Anyone? So what properties should it have? It should be variable length, and the type should be homogeneous. I said types, not type. And that turns out there are 2 types here. There's the type of the keys and the type of the values. So an example would be the successor to tally. So for example, what's a string? Hello world, my name is Tally. Okay. Let's look at this. What are all the keys here? They're strings. What are all the values? They're integers. So that's the equivalent of a list. And because I can't use the word list again, and I can't use the word association, it's too long, this is an index type. And it looks like this. Index type, in this case, it would be string type, arrow, integer type. And it formats as this little guy here. So that represents, an association that has all the keys are the same thing, all the values are the same thing. All right, okay, now let's build these guys up. So we've got the atoms, we've got the compounds, and we can now start building complicated types. And I will show you an example. So let's have a struct type. Oh, I forgot to mention, what is the type of this? This is a struct. So this is an index type, the fixed length case, and the variable length case, and the fixed length case is the struct. Okay. So let's write down the struct for a person. So age is an integer type, name is string type, height is integer type again, and we could conceivably attach quantities to these. That would be fine. And then sex. Sex is enum type, M versus F. Okay, it didn't format nicely, but let's try plain type form. What? Oh, this needs to be an association, that's why. Good, and I think this should format nicely. Yes, it's got this weird, mathematical style format here. It's like, subscripts on the indices of this tuple with the names. Height, name, height, age, name, height, and sex. Okay, now for some cool stuff. We can synthesize examples of this type. So we can say random variate of, this is person, and we can just keep doing that. Now, the name is kind of stupid. So Nile, that actually is a reasonable name. But Nyoftowetu is not a ergor. Okay, anyway. These are synthesized from a bigram model of English, by the way. Okay, so to help us have non-stupid examples, we're going to add some metadata to one of these types. So here we have name. I'm going to say property, string type, generator, random name. Yeah. Is that a valid type? Plain type form. Oh, it didn't go inside. I was expecting it to go inside. Okay, no problem. We'll just do it manually, which is scalar type of string. There we go. Good. And if you're curious, in the input form, the only reason the input form is a little bit different because it has this space for metadata. And the scalar type string has got this little extra bit of metadata there saying the generator is random name. Okay. So let's do this. Okay, Wyatt Sanchez. That's a cool name. Anyway. And we can synthesize really complicated examples. So a little bit more complex example here would be 50 of these people. Now here we're getting into the realm of kind of like SQL and databases. You can imagine this as like one table in a SQL table. As if we had enough metadata about which are the keys and what are the values of the constraints on these things, and can this be nullable? Now this is enough to sort of model the first tier of sort of databases. Okay. And the last things that I may or may not cover is it's easy to check whether things obey a certain type. So you can say, here's a real piece of data. Does it obey this type constraint? And something I haven't shown so far is that you can actually infer types. So you say infer type of data. It has deduced. This could be a trick, of course, but I'm not tricking you. It hasn't seen data. It doesn't know about data, even though it generated it. And it's looked at these guys and kind of deduced that they all have a similar thing and inferred that. Although it didn't catch that sex was, that's how you tell I'm not cheating. This was an enum that takes on values male and female, but it didn't deduce that this was an enum here. I don't know why. It should have, actually. Okay, so I've discussed types in a little bit of detail. Okay, so now transforms. So now that we've got to this type machinery, we can start answering the question, what are the big guns? We can bring out the big guns now. We have ammunition. What are we going to fire here? And the idea is that I'm not going to talk at all about SQL. Like, that's a complicated story, how we link this up to this particular way of doing things. But in the world of like NoSQL databases, one of the things that makes them really powerful and friendly for people to use is the fact that they're hierarchical. And it's very natural to express queries that interest you. It's like step by step by step, you're kind of going inside a tree. It's easy to reason about. You can see the tree. It's human readable. The relationships are clear, but it's not quite as powerful as the world of relational databases in SQL, because there's certain kind of relationships you can't express in a hierarchical form. And it's kind of similar to how, if you have like a torus in some mathematics, a torus, you can kind of like zoom in on a little piece of it, and it looks Euclidean, but the whole thing cannot be described in a Euclidean way. You have to kind of patch things together by looking at pieces at a time. And it's sort of very similar to what one's forced to do when trying to see SQL as sort of hierarchical data, relational data as hierarchical data. So let me show you a transform. So we all know about part syntax and something like, first let's make some interesting data. Okay? I want this to be like audience participation time. Give me something about the world that we should try to model. Someone suggest something. Okay, nice and creepy, thank you. All right. So let's imagine, how do we even get started on that? Okay, so we had an email. Let's model a single email. Okay, so an email has, remember it has to be, I've sort of brushed under the rug how we take relational data and sort of format it as hierarchical data. Trouble with emails, it's so relational. Me sending an email to you, you back to me, it's a little bit awkward, but I'm just thinking, what about contact details? That's maybe a little bit better. Okay, so let's have address book. An address book is a struct. No, it's a list of structs. So it's a list type of struct type. Each entry in the address book will be a bunch of things, right? A name, which is a string. A address, I guess. Let's call that a string too. Phone number. Let's be optimistic and call that an integer. And a, what else? Email address. And we can imagine constructing an email address type. That's interesting, yeah. Email address, let's construct a type for that. So let's say struct type. It could even be tuple, because it's, it would be nice to name them. Okay, so what are we going to break it up into the sort of prefix and then like the provider? How about that? So we're going to do a prefix, arrow string type, and then provider, arrow enum type. And let's imagine that, this is probably true, there's really only 2 games in town. Yahoo. Ooh, small friend. Yeah. Why is this happening again? Oh yeah, because I need to add a association there. Okay, that's our model of an email address. And now we can go put that guy there. And we've got a list of those guys. Okay, that's an address book. So, let's see, address book. Looks good. Random variant of this. Let's make one address book. And let's do the whole generator trick. So, scalar type, string, generator. Gapo. Yeah. 6, phone number 6. That's terrible. Anyway. Well, we can ask, like, who's got the same phone number, which is fun. Okay, let's call this book. Now, this is cutting-edge stuff. I'm working on it every day. I can't keep my hands off it because it's so much fun. This may or may not work. I can't make any promises. Let's find out. 5 minutes left. Okay, awesome. So, the way to think, so we've got this, let's see the Look at the address book type again. Okay, so we've got a list of tuples, of structs. Name is a string, address is a string, I is a phone number. Okay, how about we try to get out all the phone numbers? I mean, you could even do this with part syntax, right? And transforms inherit a lot of stuff from part syntax. So let's say all the addresses, and we want the field address. That should work. Oh. Well, this is version 9. I have to kind of fake it a little bit, so. Okay. God, that doesn't even work. Why not? Oh, okay. Ah, okay. So let's make, let's add a bit of metadata here. Let's say length goes to 100 here. Okay. Cool. So we've got a list of names. That's so far so ordinary. Okay. Now let's, I mean, this will even work with part, I think. No, it doesn't. Okay, now let's try with transforms. So a transform is sort of similar to part spec, but it kind of encapsulates computation as well as lookup. So we can say all the addresses. Now, this is itself an object. This represents a transformation. Like, these things are rich enough that you want to ask questions about them, like visualize them, reason about them in their own right before you actually do anything with them. So can anyone see that? Can you read that okay? Can you see that? Okay. So here at level 1, which we don't know what the name is because we haven't attached this to anything yet. At level 1, we're going to take everything. And at level 2, we're going to drill down into a specific field, the address field. At level 3, so address is now a string. Let's say we want to map string length across this. Okay. So now we've got level 1 then we're taking part of that. And at level 2, we're mapping string length. And this little diagram indicates us the sort of path that we're taking through this data structure. On the way down, we're just going to go through everything, going to drill down. Then on the way back up again, we'll call string length on the strings. And then finally, we'll end up with, similarly, a list of these guys. So let's try apply this to address book. To book. Okay, there we go. So now this is very simple stuff, but it's the beginning of what you can do with transforms. And I just closed it for some reason. But we can also look at. So I'm over time, right? Yeah. Okay. So if people are intrigued by this, there's some really awesome stuff you can do with transforms. Come talk to me, and I'll kind of demo it in the hallway or something. Okay. Cool. Thanks.